So f of a plus delta x, which is this height here, can be closely approximated by the value on the tangent line at the same location, a plus delta x. So we should be able to write this up a little bit here. F of a plus delta x can be approximated by this derivative, right, with x minus a plus the original function value, i.e. the tangent line, should have f prime a x minus a plus f of a, where instead of x here, I would have in a plus delta x, right? So this value here is really a plus delta x at this point. Now delta x is really the same as dx, right? The differential of x is the same as this, this actual distance here, delta x. So I could replace all these delta x's with dx's if I wanted. It doesn't really matter which one I use. Okay, but this a plus delta x that we're using in here really says nothing other than, right, the picture is a little arbitrary, how far away I move from a, right? That's what a plus delta x is. A plus delta x is just a distance, right? It's another location further away from a, but not too far. That's all a plus delta x really means. So instead of me writing f of a plus delta x down here, I should just be able to write the function, right? F of x will be nicely approximated by our tangent line as long as x, the x value we'll be talking about, is near a. That's all a plus delta x is trying to say, right? A plus some small value would really just be any x value near a. And of course, it'd be exactly a, right? Or sorry, it'd be exactly the function value if x were a. If x is a itself, you see if you put a in here, this would go to 0. F prime of a times 0 is 0. I would just have f of a. So f of a would be exactly f of a. So the approximation we're using with this tangent line here is exact whenever x is a itself. And if you move away from that, it's going to be a little bit different. Right? The picture you can see. Right? Move a little further away than a itself, and now the tangent line will not be the same as the curve, right? The height will not be the same as the curve height. It'll be a little bit away. And the further away you move, right? Again, my picture was exaggerated. In reality, these are extremely close to each other. But as the further away you move, and also depending upon the concavity, right, how steep the curve changes right here, will determine how far away the tangent line is from the curve at the point you pick. And so the discrepancy will be even worse the further away you move. So that's why this approximation is only good when x is near a. Since we've approximated f of x with a tangent line, that means this is actually called the linear approximation, because it's a line. It's true it's a tangent line in particular, but since it's a line, it's called a linear approximation. Of the function f at a. Okay? It's the linear approximation of f of x at a, and it's good, again, for values around a. Since it's called a linear approximation, they use a special notation for it. They use Lx. So Lx is just the tangent line. Okay. So there's a linear approximation. They also call it a linearization. There's different phrases for it. But ultimately, it is approximation to the function when x is near a, as stated above.